All right. The second speaker is Yuichi Kitamura of Yale University. So he's a professor of economics there. He received a Sloan Fellow in 2000 and Nakahara Prize of Japan Economic Society in 2006 and became Fellow of Econometric Society in 2009. So he has made many wonderful and admirable contributions to non-parametric and semi-parametric modeling, moments restriction models and finite mixtures, empirical likelihood, and bootstraps. So let's welcome Yuichi to give a talk.
Okay. So we do this. Okay. So once again, thank you very much for having me, and so I'd like to thank the organizer and everybody else. So as the title of this paper, well, so this is a joint paper with York Story at Cornell. And so as the title of this paper says, so this paper is all about random utility models. And of course, random utility model is kind of everywhere, especially if we are doing microeconometrics. That's one of the most fundamental framework used everywhere. And of course, in actual applications of any random utility models, typically you use a little bit more extra specifications and all sorts of bells and whistles comes with it. And on the other hand, you can think that so removing all these, again, bells and whistles and conditions and some extra specifications, you can ask, so what exactly is the restriction the random utility model framework would imply on the observable data? And of course, that's, so there's an answer to that, and it boils down to the kind of restriction in terms of revealed preference relationships. And so that's at the theoretical level, that's a classic, extremely important paper or papers written by McFadden and Richter, over, I don't know, 2-3 decades actually. And so probably by now 4 or 5 years ago, we started thinking that, okay, so we can think about this really bare basic fundamental restrictions implied by random utility models and try not to add all the bells and whistles and see what's going to happen. What's going to happen if we do that? So that's the kind of simple question we asked. And so it turns out that kind of lots of things came out. And so today, I don't think I can just give the whole kind of a set of results we got. So the only thing I can do is actually to give you some flavor of what we have done and what we want to do next. So that's the game plan. So just getting into the basic. So once again, as I said before, here we are not really, introducing many, specific details. It's just a really, really basic random utility model. So what this says, except for the fact that here the U, which is of course the utility, is actually representing unobserved heterogeneity. So, but otherwise, the bottom equation down there is, of course, this is just, simple utility maximization. And so just to fix notation, so P is the price vector. And when I say price vector, I use this notation. So here I say total expenditure is normalized to 1. And so maybe you can think that this P is actually the actual price divided by the total expenditure or income, or whatever it is. And so that's my notation. If you don't like this notation, you can still keep both the price and income in this B of P function, and that's okay with me. So anyway, so that's really basic. So now, so what we observe, probably the best way to describe what we have in our mind would be we have a repeated cross-section of data of Y, the choices, and P, which is the budget set. So given a budget set, the consumer chooses Y, depending on his or her utility function U. But of course, well, okay, so let's go on a little bit more. And so first I'm talking about kind of identification, so sampling and stuff like that is not here. So then what the econometrician observed is simply this choice probability of given that price or budget set is P, and then what's the probability of the observed choice lying in whatever the set A. So that's what we observe. Now, so to be clear here, the kind of basic result we have, we assume kind of exogeneity of P, and so U, the random utility function, and P independent. Now later on, actually, we have some, oops, I did the same thing. Yep. Okay. Right. Thank you. Thanks. All right. So later on, I'm going to do a bit of what we can do when there's an endogeneity problem. But so let's first say U and P are independent. And then, okay, so let's just skip this guy down here. Now, so what's kind of in our approach, the main thing here is that the utility function is actually, it's a drawn from the population. And as Andrew was talking about, typically when we do certain applications in, say, microeconometrics, we typically say that, okay, so there's this epsilon representing unobserved heterogeneity. Whereas right here we are saying that just U, the utility function itself, is representing the whole unobserved heterogeneity. And so that's a kind of point of departure here. And once again, at the very theoretical level, there's an answer to this question that what's the kind of implication of random utility axioms on observed quantities like conditional choice probabilities. And so that's summarized by all these papers by McFadden and Richter, and typically called the axiom of stochastic revealer preference, ASRP. And just to going through a bit of literature really quickly. And so of course, there are lots of econometrics done in terms of a revealed preference, and starting off from probably the variance, many papers are very well known, but also Browning-Crawford, a series of papers, and Epstein and Yachu paper. So that's there are these papers, but these papers are almost like just take a standard, non-stochastic revealed preference theory, and then kind of sneak in epsilon somewhere and do econometrics. So that's my unfair description of what they are doing. But anyway, and there are many other recent papers on this subject. And so, for example, Blunder, Christensen, masking really does a estimation of a stochastic demand. So it includes really general unobserved heterogeneity, as well as a few papers by my co-author and Hoderlein. And so that's, I should mention that. And also Lou Bell has, with also this paper by Hoderlein, so they consider the implication of like integrability and rationality aggregate demand. So that's clearly related to what we are doing down here. When we do this analysis of fully unrestricted revealed preference type analysis to do a like counterfactual prediction, and then in terms of a spirit of the approach, it gets really close to what Mansky did in 2012, and as well as a recent paper by Hassan and Newey also does kind of a counterfactual analysis with extra like smoothness conditions. But anyway, so there are, especially recent papers, kind of getting into this literature as well. Okay, so I am going to skip this one too. Okay, so just to fix the notation, so I already said that I index the budget sets by P, and so here I say there are only finite number of budget sets considered. I'm going to come back to this point, but so let's say at this point, let's just assume that later, one of the applications we have in our mind, actually the budget is so we are using the kind of a data set where you have a income data and price data, and price data is annual, so it's kind of discrete, I mean finite number, whereas income data is actually, of course, continuum. So in a way, it's a little bit odd thing to say here that there are a finite number of P's, but then in reality what we do is actually taking like median income of each year and stuff. I don't want to get into too much details of particular applications. So right here, from the outset, I say, let's just assume that there are only finite number of budgets. And theoretically, it's not a problem to have a continuum, but it's just all the statistical theory we developed at this point, we do a finite number. Okay, so then what's going to happen is that what we observe is a bunch of conditional choice probabilities of people choosing when people are facing particular budget sets like B sub J. Now all the budget sets are just indexed by 1, 2, 3 to capital J. Okay, and then one really, in a way, it's a simple observation, but quite effective, is actually, even though right here, up to this point, I didn't say that what's the choice set for individuals. And in particular, in the applications we have in our mind, choice is actually continuous variable. However, one thing we can say is like this. So this is a kind of typical revealed preference picture you would see in any textbook. And even I don't need 3 lines to explain. So let's just use, say, blue and green here, and just eliminate red just mentally. And so, of course, what the revealed preference restriction would say is that if somebody is choosing the patch represented by G, and then the same person cannot choose A, right? So that violates the otherwise you get the cycle, and so that's not allowed. But otherwise you can do anything. In particular, as I said before, what you cannot have is choosing from G and A at the same time. But on the other hand, it doesn't say where you should be. For example, you can choose from, say, patch A if you're not choosing from G. But the location on patch A really doesn't matter. So in the end, if you are just focusing on the revealed preference restriction, you don't have to worry about where each observation is sitting on each patch. You can just say that, oh, this person chose patch A when that person is facing blue budget. Right? So that automatically kind of discretize our data set, and it's not a extra restriction we are imposing. It's just the nature of their revealed preference. So that discretization just pops out of theory. But then, so now because of this discretization, what econometrician observe now is these, for example, coming back to this picture, if somebody is facing this blue budget, and then is this person, well, what's the probability of a population choosing C or B or A? So that's the observables. But then, so this, the vector pi j right here is, it's the choice probability. So each j refers to the color of the budget. So let's say small j is blue, budget, blue. And then pi sub j vector is just a choice probability on the blue budget. So that's pi sub j. And of course, we observe, you know, finite but bunch of budget sets, blue and red and green. So in this case, capital J is 3. And then we would stack pi of red, pi of green, and pi of, I forgot, green. Did I say that? Anyway, so we stack all these budgets, and so pi is all the choice probabilities we observe. Okay, so that's what econometricians observe, and then the question we can ask is, so is this vector of pi rationalizable in the view of random utility model? So that's what we are doing. And so since I believe there's no way I can describe all these notation here, so let me kind of just skip that and just verbally tell you what exactly this matrix A is. So matrix A is a representing all the rational choice patterns particular person would be possibly choosing, if person is rational, facing, say, blue and green and red budget. Okay. And so if we totally ignore rationality assumption, and then it's just a matrix would be just the combination of all possible, you know, choices. But of course, certain choices are not allowed under the revealed preference restriction. And so this A matrix is all the matrix of all choice patterns allowed under the rationality restriction. So A actually embodies all the rationality restriction the random utility model is imposing. And then, so here's the catch. And so McFadden and Richter shows that indeed this is a very intuitive relationship. But as far as they say, this observable pi vector can be expressed as a non-negative linear combination of all choice patterns possible under the rationality restriction, and then it's rationalizable. And so nu is a little bit looking like a probability vector, and probability over the heterogeneity over the population. One thing I should emphasize here is that it's not like, so this one really looks like a finite mixture model now, but we are not saying that there are only finite types of people. Once again, this finite mixture expression comes out because all the discretization coming out of the picture, and that just gets into this. So underlying distribution of the unobserved heterogeneity is sort of continuous. Okay, and so that's the restriction we want to use. So we are saying that this relationship should happen where this delta h minus 1 just says that V is a kind of probability vector. Okay, And so we can just do a tiny bit of calculation to say that actually the V adding up to 1 restriction is kind of redundant. So you can just eliminate it. So now it says that A nu is equal to pi. If this thing can happen for a, if there exists a positive, non-negative vector such that this relationship happens, and then pi is rationalizable. And so in terms of, so now we want to turn this into a econometrics in 7 minutes or something. And so how does it go? And so Andrew had a really beautiful 3D presentation. And so I have to use my finger to do it. And so this A has a bunch of column vectors. So my fingers are representing all these column vectors. And so this restriction is saying that there's a cone spanned by the fingers, and pi has to be inside of the cone. If pi is in the inside of the cone, and then pi is rationalizable. And if pi is outside of the cone, it's not. It's as simple as that. And then if you want to do a statistics with it, one natural thing to do is project pi on this cone and take the distance between pi and this cone. And if this distance is a positive, and then it's a rejection of the random utility, I mean the stochastic rationalizability, and if it's 0, it's not. And so that's what this is doing. And so I just, once again, ignore all these things, I'm sorry. And so the test statistic we would be using is something like this. Right? So pi hat is the observed choice probability vector, and A is coming out of this theory. So you see budget sets and you can calculate A, even though I have to say that the dimension of A, number of columns allowed, can be extremely big. So even when you have say 8 budget sets, say, the potential choice pattern allowed under the rationality restriction can be sometimes 500,000, and it's an enormous number, even though it's a finite number. But still, you can do this kind of minimization thanks to a modern computer, so it's not a problem. But on the other hand, getting a matrix can be very difficult when there are a bunch of budget sets. So there's a computational issue of how to calculate this guy, but again, I ignore that. And so I just focus today on how to get a critical value for this thing. And there are many ways of doing it. So the easy thing to do here is, for example, you can just bootstrap this guy. And if you're not worried about, say, uniformity issue, and then that's okay. You can just do it. But of course, this is kind of an inequality restriction. And so you know, in the research literature, everybody is worried about uniformity restrict the property. And so in order to get valid inference in terms of uniformity, you have to do something. And one thing you can do is, for example, do a subsampling. So that's quite a versatile tool, although you might experience loss of power. And so that's the reason why lots of people started doing this kind of inequality selection method. And how long? 15 minutes? Oh, okay. Oh, I'm good, actually. Okay. So hearing that, so once again, so next is my graphic. Not next. Okay, so I can keep on going. Okay, so one method is subsampling, and so I say something here, but I'm going to explain everything in terms of a picture. But one thing I should say before showing you a picture is that, so there's this recent literature of doing inequalities selection to get valid inference when you are facing a, say, moment inequality. And that would be great. That would totally solve this problem we are facing. But the only thing which is a little bit difficult here is that, as you can see, or as you might recall, our restriction is this observed pi is sitting in this cone C. So that's our restriction. So that's what I call indirect moment inequalities, meaning that the usual moment inequality literature, you want to have some moments calculated, and you say, well, that has to be non-negative or something. But if you can, so if you see this expression, it's a little bit different. It's not quite written in this form. But on the other hand, you can convert this kind of a representation of the inequality into a standard moment inequality going through something called like the Wiles theorem. And once again, you don't have to worry about this thing at this point. And so if you can move from the standard restriction, the original restriction that pi is sitting in the cone to this kind of a restriction which Wiles theorem guarantees, and then this is easy. The last statistic really looks like a standard moment inequality testing, and you can do moment moment selection test and all that stuff. Unfortunately, moving from this indirect representation to the direct representation where you can use moment inequality moment selection method, that calculation becomes totally infeasible even with a fairly small, in our case, A matrix. Like if it's 30 by 30, it's already very hard. But right now, in our applications, we are looking at something like 500 times 500,000 dimension A. So it's no way you can do this thing. So that's the only reason why I cannot resort to this moment selection method. Okay, so what do we do? Okay, so here comes the graphics. Okay, so sorry that it's pretty ugly, but at a very generic level, we are saying that some parameter must be sitting in this kind of a set, the yellow set down here. And so just to fix the idea, even though it's not quite right, just to emphasize the case that, say, true pi is on the cusp, but let's just say it's on the cusp. So suppose true pi is over there, and we are testing whether the true red dot is inside of the yellow zone, and of course it is. So in this case, the moment inequality is satisfied. Now, so in reality, of course, we don't know where red dot is. We just observe, estimated pi. So presumably, pi hats should be around the red dot, but not quite on the red dot. So let's say it's down here. So this would be the estimate. But then, of course, we know that when you do a bootstrap, you have to impose the constraints, which is this red zone, yellow zone. So we're going to just project the purple dot on the yellow zone. And so the constraint estimator would be eta hat. And then, so the textbook would tell you that, well, you should bootstrap out of this eta point. Right? So that's what's going to happen. Now, however, if actually I knew that true red dot point is actually on the cusp, and then what's the critical value we should use? So pi hat distribution would be like all over there, and our statistic is the orthogonal projection of pi hat on the residual lengths of the residual vector of pi hat on the cone. And so whatever pi hat you get, the orange arrows are the orthogonal projection, and you calculate the length of it. And so the distribution of that length is the critical value distribution, ideally. All right, so that's, as you can see, there's some funny kind of a censoring thing going on. So it's a kind of a non-standard distribution. So that's the ideal distribution. But we don't know where red is in reality. So in reality, econometrician thinks that, okay, so I estimate constraint estimator eta hat and then bootstrap out of it. So the problem here is that so the bootstrap distribution is not originated at the cusp, but on this the region, and so the the generated critical bootstrapped critical value distribution is the vertical length of projection of all these the controls onto this thing, and so actually there's more censoring going on. And because there's more censoring, the bootstrap critical distribution would be pushed towards 0. And we use that, whereas ideally, the actual critical value distribution should be a little bit shifted toward the left. Hence, if we just ignore this problem, do the bootstrap, and then you get over-rejection. So that's a kind of a short story of what's going on. Okay, and so so one thing you can do is do subsampling, and what subsampling does is artificially inflate the variance so that even though the estimated purple dot is a little bit away from the cusp, since you are making that the variance artificially big, it almost starts to looking like the red dot is at the cusp. So that's how it works. Or moment selection people would say that, well, in this case, if eta hat is close to any cusp, and then move it there and bootstrap from there. As I said before, the problem of we are facing is that we just can't do it because of the dimensionality of the problem. So we don't know whether eta hat is actually close to the cusp or not. We have no idea, just computationally. But what you can do is, instead of, say, doing moment selection or something, what you can do is just make the restriction tiny bit tighter. So what it does is that move these blue original line into the inside, and we don't know where these cusps are, but we know that everything is moving inside for sure when we tighten all the restriction. And then if the original estimator pi hat is right there, and then after tightening the constraint, the projection is actually on the cusp. And so you can just bootstrap out of it. So that's how it works. Okay, and so that's the mechanics of it. And so you can do all these things, and you can show the like uniformity property and stuff like that. Okay, so endogeneity, just quickly. So far, I assumed that the distribution of U is independent of P, but in certain applications, that may not be a good assumption. So what do we do? And so you can just actually rewrite the whole thing in this way. So Y is actually the choice once again. And so D of P, so the choice set P, and U is the realization of your utility. So U is infinite dimensional unobserved heterogeneity, hitting the demand function. And so suppose you have a kind of reduced form, something like this. I would be a little bit ambiguous about what kind of a reduced form we want to have. But anyway, so now we allow the endogeneity. So P and U are possibly correlated. But once we write the whole thing in this way, and then it kind of looks actually like a nonparametric triangular model. And once again, Andrew has the famous paper in 2009 going after the point full identification of the structural function. But of course, in this case, you can't do, let's say, unrestricted dimensional U. So in this case, say, U is a scalar and D is monotone in U and stuff like that. But then, there are a few papers like Imbens-Newey and also Blundell and Powell review paper. So they note that actually, as far as you're just interested in average counterfactual effects, sometimes you can just get away with, totally unrestricted, potentially infinite dimensional U, which is great because in our case, U is utility function. And so, again, I'm gonna, this. So this part is nothing new in a way. It's just kind of a standard calculation done in this literature, and you can actually get the pi of the choice probability when somebody is given the budget sets, and he or she is externally given a utility function draw from the marginal population distribution of, is that 0? 2, okay. And then you can get this with a little bit of a restriction like support condition, which actually Neshe was talking about this support condition, stuff like that yesterday. And so we can do this. So that's my answer. Okay, so counterfactuals. So what do we do? So the framework, if we kind of agree on what we've seen here, and then actually the principle is the same. It's just, so suppose I want to do a prediction on, now say, choice probability or expected demand when new budget set is given, something like, new tax or whatever it is. And then the framework is totally the same. We would have A matrix, pi, and everything, except that so suppose that you add extra budget J. So that say last budget is counterfactual, and then you don't observe pi of capital J because that's what you want. But otherwise you observe everything. So the prediction region would be simply obtained by solving characterized by this set, which says that except for the last one, the pi sub minus j is the observed choice probability, and you just collect all the potential pi sub capital J consistent with the observed choices. So that's what you can do. And using that principle, you can also do a bounds analysis on the expected demand. Also, of course, if you are worried about endogeneity, and then you can add this the control function track, and then you can do a counterfactual with a potential presence of endogeneity. Okay, and you can do a confidence region for the counterfactual regions as well. It's pretty much same principle, so I don't think I have to explain it. And so pretty much that's it. And so that's what we did. And of course, you might want to do, especially the computation is very intensive, and any computational innovation that can be used in analysis would be great. So I think I should stop here. Okay.
Any questions? I'm pretty sure people all get tired. Just
yeah, well, there's a problem.
You do ask for, could you say a little bit more about the computational techniques you did use? Of course, you always hope for improvement, but could you say a little bit more about what you did use?
Yeah, so I was a little bit worried about doing this minimization to get our test statistic, because we are doing minimization over like million dimension. But it's pretty much quadratic, linear quadratic programming. So actually that's not an issue. We can do it. So I'm pretty confident that that's not the bottleneck. The true bottleneck is getting this A matrix. And as I said before, it can be 1,000 dimension times 500,000 dimension with only 8 budget sets. So if we say I have So that's really the the limits of so anything that allows us to calculate a matrix would be great. But right here we are doing a few tricks, but not something like if there are some no intersecting budget sets, and then you can exploit that kind of a property. That really saves time. But in the end, the A matrix is the key, and so that's the hardest.
Yeah, so let's thanks to Yuichi and Andrew again.